Hi, BC Calc. This is going to be our day 6 notes in your packet. So if you want to get that out and start looking at what we have for our intro to derivatives. So I know that last year at the end of pre-calc honors, you would have studied the concept of what a derivative is, and it has something to do with the slope of a curve. And what it says right at the top to get started is that the slope of a curve can vary at different points. So for example, if I pick a point at this point on the curve and I were to draw the slope at that point, it's pretty steeply negative. But meanwhile, if I pick, this point right here, the slope of the curve at that point, it's certainly positive, and it's less steep than this point was over here. And I could probably even, identify a few locations where the slope at a certain point would equal 0 and have no slope at all. So what we're going to do is we're going to analyze different ways in which we can calculate slopes to points on a curve. And one way we're going to do this is we're going to look at, first of all, the function f of x equals x squared minus 4x plus 2. And we're going to determine the slope at x equals 3 using the quote-unquote get close technique. So what do we mean by get close? Well, first and foremost, if we're going to find slope, we need 2 points, don't we? All right, isn't slope delta y over delta x? So when I do the change in y over the change in x, typically that involves having 2 coordinate pairs. So I know that we're looking at x equals 3. So one of the points would be whatever the y value is at x equals 3. Just to save us some time here, you'll trust me that f of 3 winds up being -1. So how can we find another point that's maybe close by so that this way we can find the slope eventually of the tangent line? That's what we're looking for here. Well, I'm going to pick maybe x to be 3.01. So f of 3.01, if you were to plug that into your function f of x up here, would be -0.9779. And with that value right there, we can now calculate the slope, not of the tangent line necessarily, but this would be called a secant line. A secant line connects 2 points on the curve. So the slope of the secant, change in y over change in x, the y values would be the difference, -1 minus a negative becomes plus 0.9779 over 3 minus 3.01. So change in y over change in x, and this winds up coming out to be here a total of 2.01. So if the slope of the secant line is 2.01, we chose a point super close by to x equals 3, I'm pretty confident at this point we can establish that the slope of the tangent line, which is this concept of a derivative, is equal to approximately 2. Okay, and it will be 2, and we'll be able to confirm that algebraically through future examples. So knowing that the slope of the tangent line is 2, right below it says write the equation of the tangent line to the curve at x equals 3. So the way I'm going to approach this is I'm going to use point slope form in order to do this. Point slope, as a reminder, looks like this. It's really nice to use point slope form to write tangent line equations because we'll always have a slope and a point. Right, at the point x equals 3, we recall that the y value there was -1. So combine that with a slope of 2, your equation would be y plus 1 equals +2 times x minus 3. And that's it. If you're a really big fan of y equals mx plus b, just because you like the way it looks and it's easier for you to graph it, of course, just distribute the 2 in, subtract the 1 over to get y equals 2x minus 7. Okay, so the tangent line to this quadratic, this parabola, at x equals 3 has the equation y equals 2x minus 7. And the last part says to confirm your results on the graphing calculator. So all you would really do, and we could talk about this tomorrow in class if we need to, is in y1 type in the quadratic x squared minus 4x plus 2. In y2 type in your tangent line equation and just confirm that when you're graphing this parabola here, that at x equals 3, the line 2x minus 7 is tangent to the graph. Sorry, that's a super weak sketch, but you can confirm that on your calculator on your own time if you'd like to. Moving on to the next page, we're going to now get into the formal definition of finding derivatives at any given value of x. So there's a really nice diagram at the top of the page here that illustrates what we're trying to accomplish. we're going to use the same concept that we just used, where we find the slope of a secant line. That secant line is connecting points P and Q in the diagram here. And I can use the slope of the secant line to approximate the slope of the tangent. And we'll see in a second actually where limits come into play in that discussion. First of all, the coordinates of point P would be x comma f of x. And you could tell that based on where we hit the x and where it's labeled on the y-axis. So then what happens is we go over a certain distance away from x, and we're calling that the change in x, delta x. And we get to point Q. So the x-coordinate there would be x plus delta x, as you can see marked off on the x-axis here. And the corresponding y value would be f of x plus delta x. So it's important to establish those as coordinate points, because now we can calculate what's called the average rate of change, also known as the slope of the secant. So the slope of the secant line, PQ, is going to be m equals change in y over change in x, would be f of x plus delta x minus the other y value, f of x. And then this is all over x plus delta x minus x from the coordinate of point P. And the last thing we're going to do to clean this up is that my slope, therefore, if you look at the bottom, we have x and negative x are going to cancel out. We get f of x plus delta x minus f of x all over delta x.